to related rates. Take a look at this example here. We've got the radius of a circular oil spill and it's expanding, and we want to know how fast the area of the spill is increasing. So we're relating two rates, the rate of change of area and the rate of change of the radius. Now let's go through the solution by using these steps. Step one is identify the primary equation. Well, this problem is talking about the area of a circle, so let's use A equals pi r squared, where A is the area and r is the radius of the circle. And then the most important part of step one is this line here, where you write down mathematically what you're given and what you want, because it's impossible to solve for what you want if you can't write it down. So what are we given? You might want to pause the video and just see if you can do this on your own. We're given dr dt equals 2. The radius expands, that's rate, at 2 meters per minute. What do we want? We want dA dt when r is 25. How fast, that's a rate, is the area increasing when r is 25? So what we're given is an equation, and what we want is an expression. But you have to be able to write those things down, because then step two is super easy. So step two, we just take d by dt of both sides of our primary equation, keeping in mind that both a and r are functions of t, so we're going to have to use implicit differentiation. So on the left, d by dt of a is simply dA dt, and on the right, we're going to bring the 2 down, leave the r alone, and then multiply by the derivative of the inside, which is dr dt. Now, back when we did implicit differentiation, instead of writing dy dx, we just wrote y prime. In this section, I really want you to use the Leibniz notation, like dr dt rather than r prime, and the reason is there's so many variables, it gets confusing which prime you're referring to. Okay, so now we're just going to plug in what we know. We know r is 25, and we know dr dt is 2. So dA dt at r equals 25 is 2 pi, r is 25, and dr dt is 2. So that's 100 pi. And the units, now I'm going to put the units back on for my final answer. Radius is being measured in meters. So area is going to be meters squared, and that's going to be per minute. And there's your rate. Super easy if you follow the steps. Okay, let's look at another one. We've got a 5-meter ladder, and it's sliding down a wall, and we're told the rate at which it's sliding down. And as it slides down, the bottom slides out. That green dot is sliding out. And we want to know something about the rate at which the green dot is moving. So let me jump back to the notes. Step one, let's identify our variables. We've got a triangle here. The hypotenuse is 5. Let's let x be the distance from the origin to the green dot, and let's y be the distance from the origin to the top of the ladder. All right, and so for this one, I think we want to use the equation x squared plus y squared is 25, because we're just going to be comparing the rates dr dt and dx dt. So let's see what we're given. You should pause, do the given and want on your own, and make sure you can do it. All right, we're given that the top of the ladder is sliding down at 2 feet per second. So that's dy dt. And since it's going down, I'm going to write -2. Y is getting smaller, not larger. And what we want to know the rate at which the bottom of the ladder is moving away from the wall when the base is 4 feet from the wall. So that's dx dt at x equal 4. Now note, when x is 4, y happens to be 3, because this will be a 3, 4, 5 triangle. Let me write that over here. When x equal 4, y is 3, and we're going to need that later on. Okay, step 2, we want to take d by dt of our primary equation, which is x squared plus y squared equals 25. All right, x and y are both functions of t. So for the derivative, we get 2x dx dt plus 2y dy dt equals 0. Now we're solving for dx dt. So 2x dx dt is -2y dy dt. I can cancel those 2's and divide by x to get dx dt alone. That would be -y over x times dy dt. So now that we have dx dt isolated, we can plug in what we know and find dx dt. So dx dt at x equal 4 is, well, y is going to be 3 when x equals 4, so -3 over 4, and dy dt is negative 2. By the way, if you didn't think to find y in the beginning when x is 4, now you could just jump right in now and do it using x squared plus y squared is 25. All right, so let's finish this up. This is 3/2, and the units would be feet per second. And that's a positive rate because x is getting larger, not smaller. Okay, I'm going to do one more with you, and then, well, let's just jump down and finish the lecture notes here. At the very, very end is a solved problem. I strongly suggest you do it and then read through the solution. The solution's at the end. Let's do this problem. You should pause the video and just read through this so you don't have to listen to me read. Okay, I hope you did that. The only thing we have to do is write down mathematical expressions for what we're given and what we want. We're not going to solve the problem. So we're given and want, okay? A balloon is deflating such that its radius is decreasing. That's dr dt, and that's negative 4. And we want the rate at which the volume is changing, that's dv dt, at r equals 3. That's all you have to do. And quite often on a test, I will just ask for this part right here, given and want. One's an equation, one's an expression. And by the way, you can go ahead and solve this on your own if you want and give the final answer if you do that. Okay, and let's just jump back to this one. Again, pause the video and read through it so you don't have to hear me read the sentence. All right, so step 1, we have the variables already on the picture. X is the distance from this point to Florence. 40 is a fixed distance from this point to Edison, and S is the distance between Edison and Florence. So again, we're going to use Pythagorean theorem. X squared plus 40 squared is S squared. All right, what are we given? When I read through that, I see when Florence is 30 feet from the intersection, Edison clocks the change in distance between him and Florence at 90 feet per second. So we're given ds dt equals 90. And that's when Florence is 30, that's when x is 30. So we want, at that instant, which is when x is 30, we want the rate that Florence is moving at that moment. So we want dx dt at x equal 30. So Florence is moving this way. Edison's the cop. He's just sitting there. He's clocking the distance. Okay, step 2, d by dt of x squared plus 40 squared. I'm just going to leave 40 squared as it is for now. There's no reason to evaluate it. That's d by dt of s squared. So 2x dx dt. Sure enough, the derivative of 40 squared is 0. It's a constant, so I don't even need that. That's 2s ds dt. So dx dt, the 2's cancel. That's just, whoop, there we go. Cancel the 2's, not the s. So dx dt is s over x ds dt. Okay, I'm running out of real estate here. dx dt, this is the final step. We're going to plug in x is 30. That's equal to, we want s over x, so x is 30. Now we don't know s. So we come back up here and we say, okay, when x is 30, and this is always 40, we solve for s. So that's a 30, 40, 50 triangle. You can do that in your head, or you can use the Pythagorean theorem to get that. So S is going to be 50, and then ds dt is 90. So that's 1,500, and the units would be feet per second. So the units for linear, like distance, you're going to get feet, area, feet squared, and volume would be feet cubed. Okay, and that's the end of this section.